Okay. All right, you're almost done. And there are half of you left, so not too bad. Yeah. Yeah, exactly. So yesterday we got as far as writing down this bosonized form of the interacting fermion Hamiltonian. And I'm just going to copy this down. So it was Vf over 2 integral dx. Now 1 plus 4 delta over pi sine kf a naught. And then we had the dx phi squared plus dx theta squared. And so theta, remember, was this dual field. So phi right minus phi left. Yeah, and then we had this total derivative term. So, okay, that's as far as we got yesterday. Now we'll massage this a little bit, get it into a nicer form. Now, firstly, as I already said yesterday, you might say, okay, so this one is a total derivative, let's just drop it. That would be a little bit too naive. So a better way of treating this term is to do canonical transformation. So remove the last term by shifting the field. So we take phi goes to phi minus 2 delta divided by pi to the 3/2 a naught cosine kf a naught x. So, and theta goes to theta. Okay, and essentially the idea is, if you look at this term here, after this field redefinition, you pick up a term sine kf times cosine kf, which precisely cancels this one here. Okay, so that's the idea. Yeah. So you can remove it from the Hamiltonian, but this does something interesting. What does this do? So now we remember that the lattice fermion operators were related to these bosonic vertex operators like so, e to the I kfx, and then here we had eta divided by 2 pi a naught square root, e to the minus I square root of pi phi plus theta, and then we had plus e to the minus I kfx eta bar 2 pi a naught e to the plus I square root of pi phi minus theta. Okay? And now the point I'm trying to make is if I do this field redefinition, yeah, I change what is sitting here. And I pick up a term which is proportional to x. So what the term does, it shifts kf. Okay? So in other words, what this last term does, it looks like a total derivative. You might have thought it does nothing. What it actually does is it shifts the Fermi momentum by order delta. So the extra term, the derivative term, shifts Fermi momentum so kf gets shifted to kf plus 2 delta h divided by j pi a naught. So something like this. Some shift. Okay? All right. Do I drop? Yeah. So this shift kills this term. Yeah, because once again, so if okay, so say phi of x is okay, so call this phi tilde or something like this. Yeah, so if you plug it in here, so you pick up something that would be dx phi tilde squared plus a cross term, which is dx phi tilde times cosine times sine, which precisely cancels this. Yeah, so it's no longer there. Okay, so now this term is gone, yeah, after this field redefinition, and here we have now essentially a free compact boson, but we have this extra factor here, which we would like to remove, so we remove it by another field redefinition or canonical transformation. So we say, now I want to define it as phi tilde, which is why I didn't want to call it phi tilde there. I define a new field. Phi tilde is 1 plus 4 delta divided by pi sine kf a naught to the quarter phi. And theta tilde is the same with minus a quarter theta. Okay, and so you can check that this is a canonical transformation. Okay, so this dual field, it's related to the canonical momentum. So if you do this rescaling in this way, it's a canonical transformation. And after this, the Hamiltonian now takes a very nice form. So I have a slightly changed Fermi velocity, dx, and then here we have a dx phi tilde squared. Okay, so you can put the normal ordering if you want, plus dx theta tilde squared. Okay. Yeah, so theta I defined for you a few lectures ago. So theta of x was phi right of x minus phi left of x. And phi of x was phi right of x plus phi left of x. And I said, so this has a name, it's called the dual field. Yeah. Okay, so here I have this parameter Vf tilde, which is this characteristic velocity. It's just Vf times 1 plus 2 delta over pi sine kf a naught plus order delta squared or something like this. And now phi tilde is now a compact boson. But by doing this rescaling of the Bose field, what we have done is we have changed the radius of this compact boson. So we started with the radius being 1 over square root of 4 pi. But by rescaling this, now it's no longer 1 over square root of 4 pi. Yeah, the target space of this boson. Yeah. No, well, first, yeah. No, so this multiplies this plus this. Because this term I had derived explicitly, it came from h int. So there we had a piece which was dx phi squared. We did not have a piece in h int which was a dx theta squared. Sorry? I haven't started. Okay, so here we have Vf times dx theta squared. Here I have a renormalized velocity times dx theta tilde squared. Yeah? So, yes? No, it's because, no, I understand. If you, but, okay. Delta is very small. Yeah, so if I square this, it's 1 over 4 delta, or 1 plus 4 delta over pi. Because I have rescaled by something which is to a power 1/4. So once I square this, I get this factor to the power 1/2. So I have to take the square root. Yeah. So I just use that delta is small, and so it's all hidden here. So I could have left the square root, but life is short. Okay, so I'm just writing this to the first order. I'm going to do a much better job in 10 minutes. Yeah, I'm going to give you the full answer. But so at the moment, we're still doing this pedestrian approach. So phi tilde is a compact boson. Yeah, so phi tilde, I have to identify with phi tilde plus 2 pi r tilde. But as I just said, so r tilde is no longer 1 over root of 4, 1 over square root of 4 pi. Because of this rescaling, I get this extra factor, 1 plus 4 delta over pi sine kf a naught to the quarter. Okay, and if I wanted to keep it just to the first order in delta, I would rub this out and erase the 1/4. Okay? So now, just to summarize, so we started with this interacting fermion theory, yeah, and then we used this bosonization technique. Now we have shown this interacting fermion theory is equal to a free boson. And in the free boson, we have two parameters: the compactification radius of the boson, yeah, so this r tilde, and the velocity of the boson. Those are the two parameters. So, okay, so it requires a little calculation. So if you essentially have something like this: dx theta is proportional to dt phi. That follows from the equations of motion. And remember, dt phi was proportional to the canonical momentum of the field. Okay? Okay, and now the last piece. The last piece is, okay, so it's customary to introduce what's called a Latinger parameter. in lieu of this compactification radius. So this is defined as k equals 1 over 4 pi r tilde squared. Okay, so this is basically in all the literature what you find. So then we have bosonization identities. The right moving Fermi field is this Klein factor square root 2 pi a naught e to the minus I square root of pi k phi minus I square root pi divided by k theta left of x equals eta bar 2 pi a naught e to the I square root pi k phi minus I square root pi over k theta. Okay, and this is basically what we spend all the time doing to obtain these formulas. Because now in practice, the way you use this, if you have some interacting spin model or interacting fermion model, you just use these identities to map it to some compact boson with some perturbation. Okay, so the way I have approached the problem, so I wanted to do this first. Okay, so the way I have approached this problem, I have assumed that delta is small, so I had weakly interacting fermions. Now, I'm going to tell you shortly that this framework is much more general. It actually holds also for larger values of delta, so it holds in this entire phase which I, of the phase diagram, which I had called the Luttinger liquid regime. So I had drawn for you earlier this phase ground state phase diagram of this XXZ chain, and I had said there's this phase here, which is a Luttinger liquid phase. And the description I have derived for you, literally, I showed you holds here, yeah, for small values of the interactions delta, but one can prove actually it's valid in this entire phase. And the only modification that is required is you have to adjust the two parameters of the free boson, the velocity and the Luttinger parameter. So different points in here are characterized by different velocities, different Luttinger parameters, but the same bosonization formulas, etc., hold, and you have the mapping to the free boson. Okay? Now, before I'm going to give you a little bit more details for that, I have to do one more step, because remember, so we started with a spin model, did the Jordan-Wigner transformation, got the spinless fermions, and then we bosonized to get the boson. But I'm actually not really interested in these interacting fermions. I'm interested in the spin model. So what I want to do is I want to compute correlation functions of spins, not correlation functions of fermions. And that's a difference because, as you remember, the spin operators were related to the fermion operators by the Jordan-Wigner transformation, and there was the Jordan-Wigner string, this non-local object. And what I still have to do for you, I'm going to do that now, I'm going to basically tell you, I'm going to show you how to map the Jordan-Wigner operator to the compact boson. Yeah? Okay, so the next one is bosonization of spin operators. Okay, so there's an easy part and there is a difficult part. So the easy part is SZJ. because SJ is actually local in the fermions. So this was C dagger J, Cj minus a half. Yeah. And okay, so how to bosonize this we already understand. Yeah. So C dagger J, Cj basically becomes something like R naught, right dagger right, plus left dagger left. Again, in order to define this, you have to point split and subtract, plus e to the minus 2i kfx, right dagger left, plus e to the 2i kfx left dagger right. So something like this. Okay, and these we all know how to bosonize. We have already done it yesterday. So I can just write down what the bosonic expression for Sz is. Okay, so what we get is Szj has a constant piece. Yeah, that's a piece proportional to the identity. It's clear that has to be there because I've put a magnetic field. Yeah, and so the ground state will be magnetized. There will be a finite magnetization. And in terms of the operator, that's just whatever the magnetization is times the identity. And then I get various different contributions. There's this one here, smooth contribution. Okay, so something like this. Okay, and I left the R tilde there. All right, I mean, which is kind of, doesn't matter now. Okay, plus I, some coefficient, eta bar divided by pi. And here we have sine square root 4 pi k phi minus 2kf x. So that is the bosonization of the spin operator, Sz. And you see there are basically three contributions, if you wish. There's one contribution, which is the smooth magnetization, yeah, because there's no oscillating factor in X. Yeah, so if I would sum sigma z over a largish interval, yeah, so then I would pick out this contribution, yeah, because it's smooth. There is no rapidly oscillating factor in X there. Whereas here, I have two contributions that oscillate with e to the 2i kfx and e to the minus 2i kfx, yeah. And so these are related to this right dagger left and left dagger right, yeah. And in zero magnetic field, kf would be pi over 2a naught, yeah, and this would turn out into a factor minus 1 to the j, and this would be therefore the staggered component of the magnetization. Okay, now, so the naive calculation gives that this coefficient here b is 1, but we'll see later that this cannot be trusted. In general, yeah. So this is another non-universal piece of information. Yeah, so it's actually known how to compute this for the spinor half chain, but you cannot do it. Let's say if you want to know what it is here at this point in the phase diagram, you cannot compute it in this simple way as we have done it, yeah. The formulas I derived for you in the limit of small delta. Yeah, but then I said the result is much more general. Okay? But then, if you use it much more generally, in these operator equivalences, you pick up extra factors which are non-universal, depend on the details of the lattice model, and you have to determine it by some other means. Okay? And so this coefficient here, it's some non-universal number, it depends on delta and h, and you cannot compute it in a simple fashion. Okay? Yes, 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 yes. But I'm no longer interested in delta small. I only did this in order to explain to you how to get the answer. Now that we have the answer, we will use this much more generally. Good. So then that was the easy part. So now the more interesting part is S plus and S minus. And that will show you a little bit more how to manipulate these bosonization formulas in practice. So that hopefully will be quite instructive. Okay, now let's look at S minus J. Okay, using the Jordan-Wigner transformation that I had written, I don't know, a few lectures ago. Looks like this: e to the I pi sum L less than J, C dagger L, CL, and then we had a CJ here. Okay, so now we know how to bosonize this guy here, but what about this string operator? Okay, I'm going to show you now how to do that, and it's slightly subtle. So the first step is, let's call this operator W here. The first step is, well, W is in fact a Hermitian operator. Okay? Because the eigenvalues of C dagger LCL, they're integers, yeah? So, but it doesn't look Hermitian on the face of it. So it's important for what I'm going to show you now to make this explicit. So e to the I pi sum L less than J, C dagger LCL. And then here I add the same with a minus. So I haven't really done anything, yeah, but writing it in this way will avoid some confusion a little bit later. Okay. Now, we know, in fact, how to deal with this operator in bosonization. Okay, so let's write it like so. First of all, so we have L less than J, C dagger L, CL. I call this normal ordered, and I subtract the expectation value in the ground set of the free theory. So this is the kind of thing we had done before for small delta. So I'm using the same kind of philosophy now. So assume for now delta is small. Then we get an answer, and the answer again will be generally correct even when delta is not small. Okay, so now what we do is we take this object and just bosonize it. So we say L less than J, C dagger L, CL is something like integral from minus infinity to x dx prime. So at this point I drop boundary conditions. I assume I'm in the infinite volume, no longer on a finite ring of length L, and so on and so forth, just to make life a little bit easier. Okay, and then how to bosonize this operator we know. We have done this before. I'm just going to write down the answer. So k over pi dx phi tilde. And then we have plus eta bar pi a naught squared sine 4 pi k phi tilde minus 2 kf x prime, something like this. Yeah, and you can take this normal ordered if you want. Okay, it doesn't matter. Okay, so this you get by bosonization. Okay, and now what I will do is the first term, I just integrate it, and I drop the contribution from minus infinity, yeah, because it's a total derivative. So I say this is essentially minus k divided by pi phi tilde of x. And this term I will again drop, okay? And the argument is the same we had before because I have this rapidly oscillating factor, 2k of x. And so once I integrate, I basically say I have this smooth operator with a rapidly oscillating factor, so it basically integrates out. Yeah, so we had done that before for the Hamiltonian. Basically everything was fine. Here it's a little bit more subtle, yeah, because I integrate not over the entire line, but only up to x. And this argument that you can just drop this, of course, breaks down close to here. So in principle, you can say, well, maybe I should be a little bit more precise in the way I treat the upper integration boundary. But okay, so for the purposes of making this argument, we don't, we just drop it. So phi tilde, so yeah. Okay, so I want to do this, and that suggests, yeah, so take this as an argument that suggests an answer for you, that W, so the string operator, should be 1/2 e to the minus I square root k pi phi tilde plus I kfx plus the Hermitian conjugate. And that's basically where I wanted to go. Okay? So what I just have shown you, let's say it's a plausibility argument, so it tells you what the string operator should look like. So you basically say it should look something like so. And that turns out to be the correct answer. Yeah. So if you do a better job, so this is what you get. Sorry? Because I had extra factors, yeah, so I had this piece here, which is a constant, yeah. And if you go up to j, it gives you the kfx, yeah? So this is where it comes from. Okay? No, I actually should have done it like this, so this is fine. So now we can put everything together and write down bosonization formula for S minus. And okay, so I've written W. Okay, and then this gives us that S minus J is minus 1 to the J times C times e to the I square root pi over k theta tilde. That is one piece, and then the other piece is plus minus 1 to the J A e to the 2I kfx e to the minus I square root pi k phi tilde minus I square root pi over k theta tilde. And then we have the other piece there. Okay, so this is what comes out. Okay, so I should have said, so once you know how to bosonize the string operator, you still have to multiply it by the bosonized formula for the Cj, because we know what this is in terms of bosonization. We know what this is in terms of bosonization. Once you multiply the two, you get this. Okay, and what I've done there, I have some amplitudes here, which I call A and C. And again, these you cannot really reliably compute by these kinds of arguments. So these are non-universal and depend on details of the lattice model, so on what delta is, what J is. Good. I started 10 past, right? Yes. Yeah, okay. So I have 10 more minutes. Yeah, okay. Okay, so now the next step is we know how to bosonize the spin operators. So I've shown you explicitly what the formulas are. Now we can use it. So we can use the formulas and work out what are spin-spin correlations in this Langer liquid phase of the XXZ chain. Yeah. And there was a lot of overhead, so we had to go through all of these kind of considerations, manipulations to get these bosonization formulas. But once we have them, now it's very, very easy to compute space and time dependent correlation functions. And so this is why this is really a good approach. So now let's look at correlation functions. Of or in the XXZ chain. Okay, so for example, let's look at the ground state correlation functions of SZ, J plus L, SZJ, ground state. Okay, so I will have three terms. I will have an m squared plus a naught squared k divided by pi dx phi tilde of t and x dx phi tilde of 0 and 0. And then we get plus b squared over pi squared sine square root 4 pi k phi tilde of t and x minus 2 kfx. And then here we have sine square root 4 pi k phi tilde of 0 and 0. Something like this. Okay, just using the bosonization formulas explicitly now. And now these correlation functions here are space and time dependent correlation functions in the compact boson, but those we know how to compute. I showed you before. Yeah. So this one I just can compute from the mode expansion. This one I can express in terms of two-point functions of these bosonic vertex operators. We also worked out what those are. So I know what this is, I know what this is. Yeah. So I can just now substitute this in, and I get an answer. It's very, very nice. So this has a constant piece, which is magnetization squared, and then we have plus k divided by 2 pi squared, a naught squared, x squared plus vf squared t squared, x squared minus vf squared t squared, plus b squared over 2 pi squared cosine 2kfx, and then here we get an a naught squared divided by x squared minus vf squared t squared to the k. Okay? And so that's a very powerful result, because by doing this, now in the end, we very cheaply got the result for the space and time dependent correlations in the spin model. And these are very difficult to compute by other methods. Okay, so in terms of kind of like field theory considerations, you basically can see this piece here, corresponds to a correlation function of some scalar operator, because it just depends on x squared minus v squared t squared. Yeah, whereas this one here, it corresponds to correlation function not of a scalar operator, but an operator that carries Lorentz spin. Yeah, because it depends not just on x squared minus v squared t squared, but also on x squared plus v squared t squared. And this is, you can basically just see here, because it's a component of a Lorentz vector. Okay. Now we do the same for the transverse correlations. And of course, once I have this, the way people use this originally, let's say, here you have now the space and time dependent spin-spin correlation functions. And what I told you in the first lecture, what they measure, what experimentalists measure for these quantum spin chain materials, is this dynamical structure factor, which was related to the Fourier transform of spin-spin correlation functions like these. Yeah? And then what people did is they basically took these expressions and Fourier transformed them and compared it to what they saw in elastic Newton scattering. So this is one of the uses of this thing. So now let me just write the other one, S minus, I wrote it like this, J plus L of T, S plus J of 0. Okay, so from bosonization, this is C absolute value squared minus 1 to the L a naught squared x squared minus vf squared t squared. And when I write vf in these formulas, it's really vf tilde, but you know, life is too short, so I dropped the tilde, but to be like super precise, I should keep it. 1 over 4k. And then I have plus a absolute value squared minus 1 to the L. Okay, a naught squared x squared minus vf squared t squared. 1 over 4k plus k. And then here I get an extra piece, e to the 2i kfx x plus VFT divided by x minus VFT plus e to the minus 2I kfx x minus VFT divided by x plus VFT. Voila. Okay, so those are the answers for the spin-spin correlation functions in the spinor half chain. Those are all of the spin-spin correlation functions. So why don't I have to consider, I don't know, S plus, S plus? Hmm? Nope. What does that mean? Yes? Yeah, okay. So in other words, this is 0, yeah, because of particle number conservation or by U1 symmetry. So we had spin rotational invariance around the z-axis. If I rotate around the z-axis by some angle, yeah, so then S plus picks up a phase factor. Yeah, so therefore this correlation function under U1 transformations would not be invariant, so it has to be 0. Okay, so that's why these are the only ones I have to consider, the S minus, S plus, and the S plus, S minus is just the complex conjugate of this. Okay, now what about if okay, so these 2-point spin-spin correlation functions are the most interesting ones because they relate to neutron scattering, but now let's say I'm interested in some other experimental probe and I want to compute 4-point spin correlation functions. So now what do you do if I were to give this to you as a homework problem to do this afternoon? So let's say I were to give you a homework problem, compute SZ, 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 SZ. Or if this is too easy for you, I mean, so then we can also talk about S plus, S minus, SZ, SZ. There is some truth in what you say, but the spin model is not a free theory. So I do not have a Wick's theorem at the level of the spin operators. But you're going in the right direction. So what do I do? And then you use Wick's theorem, exactly. Yeah, so you can bosonize all of these. So this gives you something involving a bunch of vertex operators and a bunch of dx phi's. But that's in the free boson theory. That's a free theory. There is a Wick's theorem, bingo. So you can just compute it there. Yeah. So basically, this bosonization framework now allows you to compute any correlation functions that you want. So we're going to take the break now. We're going to take the break now. So, all right. now, okay, so the final stretch. Okay, so now, as I already mentioned, so this description works quantitatively in the entire, what I call the Luttinger liquid part of the phase diagram. So we have this phase diagram, H versus delta. I've already drawn this for you 23 times. So I do it a 24th time. So in this entire region of the phase diagram, this bosonization formulas apply. The only caveat is the Luttinger parameter, yeah, which we had worked out explicitly for small delta, becomes a function of the magnetic field and the anisotropy delta. And the velocity similarly becomes a function of h and delta. Okay? A0, yeah. So Kf also becomes h and delta. So A0, if you wish, the way I've put it in the formulas is this converts between the field theory and the lattice model. We always had x, which was the coordinate in the field theory, was j, A0. Yeah, and then the A0, if you look at the bosonization formulas, et cetera, you compute correlation functions. The correlation functions for the spin operators I had written, they always only depend on x divided by A0, which basically brings you back to the lattice coordinate. So this is all kind of good. I think what Werner is trying to ask is something more subtle, which I'm going to address shortly. So A0, the way I've introduced it, is just the lattice spacing, but there is an ultraviolet cutoff that has to do with the low energy projection to just low energy degrees of freedom. So that's not directly related to A naught. In other words, the Luttinger liquid description, it holds at low energies, large distances. So large distances larger than some scale. Yeah, that scale, okay, so the distances certainly have to be larger than A naught, large compared to A naught, but depending on what delta is, they have to be much larger than A naught. And I'm going to tell you a little bit how you see that in a moment. So I think that's basically what you were trying to ask. So I'll come back to that. Now, the good news is these three functions, they're known exactly for the spinor half chain. Yeah, so you can derive these from what is called the Bethe-Ansatz. So I could give you another lecture or two about how to do that, but life is too short. So I'm just going to give you the answer for zero field. Because in finite field, there is no simple expression of these. For finite field, they're given in terms of the solution of some Freitorm integral equation, some linear integral equation, but there's not a simple explicit expression. So for magnetic field equal to 0, what do they look like? So Kf A naught would just be pi over 2. Yeah, and Vf would be J A naught over 2. So you see the only thing that appears here is the combination J A naught, because in the scaling limit J goes to infinity, A naught goes to 0, but this is kept fixed, times sine pi divided by 2k divided by 1 minus 1 over 2k. And finally, k is just pi divided by 2 arc cos minus delta. So these are exact. And this basically tells you what is this Langer liquid description along this line here. Yeah, and what I'm going to do now is I'm going to discuss for you a little bit. So what is the physics that we see there? Okay. So now delta equal to 0 we solved explicitly. So there we understood everything. Yeah, that was the free fermions. So K was 1. This was free fermions. Yeah, and VF was just JA naught. Okay, so there I'm not going to say anything. Now delta equals 1, yeah, which is this point here. That's a very interesting point. Okay, so here we have K equals a half. So this is called the XXX antiferromagnet. Not because of what you think, it's just because there the anisotropy vanishes. Yeah, so the interaction in the Z direction is the same as in the X direction. So VF is J A naught pi over 2. Okay, and so here you have an enhanced symmetry. So here you have an SU2 symmetry of the lattice model. Yeah, because the interaction is just S dot S. So you clearly have full spin rotational invariance. And you see this in the free boson theory because the compactification radius takes a special value. And for a special value of compactification radius of the free boson, you have this enhanced symmetry, the SU2 symmetry. Finally, delta goes to -1. What you see there from here, that the Langer parameter actually diverges. So K goes to plus infinity. And so this is the limit towards the XXX ferromagnet. And here, the velocity actually goes to 0. Okay? So now, why do I call this a ferromagnet? Okay, so let's start with that. So the model I had was H equals J, J equals 1 to L, Sxj plus 1 plus Syj plus 1 plus delta Szj plus 1. That was my Heisenberg model. Now let's set delta equals -1. Then I have this. Okay. Now what I can do is I can just do a rotation around the Z direction by pi. Yeah. And I do this on every other side. Yeah. And by doing that, I flip the signs of these two terms. Yeah. So the canonical transformation would be S tilde 2j is minus S 2j xy. Sz 2j equals Sz tilde 2j. And then on the odd ones, I just keep them the same. Yeah. So I can do this. It's compatible with SU2 commutation relations. And now you see in these products, I always have one on an even side, one on an odd side. So the Hamiltonian becomes minus j, sum over j, s tilde x, s tilde x, plus s tilde y. Well, really it becomes s tilde alpha dot s tilde alpha j plus 1. And that is precisely the SU2 invariant ferromagnet. Okay, so this is why delta goes to minus 1 goes to a ferromagnet. And of course, the physics of the ferromagnet is very different, yeah, compared to the antiferromagnet, because in the antiferromagnet, I'm going to write it down explicitly in a moment, so spins have a tendency to anti-align, yeah. The strong correlation, if this spin is up, the next spin is down. Whereas for the ferromagnet, they have a strong tendency to align. Yeah, if this is up, then the neighboring is also up. Okay. Now, let's talk a little bit about the physics. Okay, but it's gone. So, yeah. I can write it later again. So, the dominant correlations of the model are what? So I had told you before, it's a one-dimensional model at 0 temperature, so there cannot be long-range order. Okay, so there cannot be like nail order or stuff like that. So the way we classify different phases, so to speak, we look at two-point functions instead of one-point functions. One-point function would be like an order parameter. We look at two-point functions and we ask which two-point functions decay the slowest. Yeah, and that tells you what is the physical nature of the phase. Sorry? I'm on the line between minus 1 and 1. Okay? But I'm discussing the concept of quasi-long-range order. Yeah? So the dominant correlations are between the transverse one, yeah, S minus S plus, or Sx, Sx, Sy, Sy. And they are antiferromagnetic because they have this minus 1 to the L, and here we have L 1 divided by 2K. Okay, having the bosonization formulas, now we can compute all of these two-point functions, and we can ask which ones decay the slowest. Yeah, and the slowest are these. Yeah, and then you see there's this factor minus 1 to the L, so that tells you spins have a tendency to anti-align. So the pattern you get basically is like an antiferromagnet. Yeah, yeah. And you see how strongly these are correlated. That depends on this Ladinger parameter. That depends where on the line you are. Yeah? So this we call quasi-long-range order. Okay? Because the spins, they cannot freeze because they're in one dimension. Yeah? So there cannot be a nail order parameter. But the correlations can be very strong and decay very, very slowly. You see, and if you wouldn't have this factor, you would have long-range order. Okay? Now, these are the physical properties. Now I want to discuss a little bit more the corners of the phase diagram. So I want to discuss what happens here, because it's very instructive, and I want to discuss what happens here at these 2 points. So I'm going to start with delta close to 1, and then I'm going to tell you something about delta goes to minus 1, but that will be a little bit advanced. So delta goes to 1. This we can understand fully on the basis of what we have done. So H is equal to 0 still. So now remember, Kf was pi over 2a naught, because we're in zero field. When we bosonized, we had this operator, which was a cosine square root of 16 pi phi minus 4kfx. We had generated this when we were bosonizing the interaction of the interacting fermion model, and then we had said we can drop it in finite field, or we can drop it when beta, so to speak, so the dimension of the operator is sufficiently large. And it turns out the perturbation along this line, it's irrelevant in this entire regime, but it becomes marginal at, so the beta becomes square root of 8 pi at this point, and it becomes relevant here. And that's precisely the physics we had discussed when we were discussing the Kosterlitz-Thouless transition. Okay, so now let's write it down. So this tells us that 4kf a naught is 2 pi. And this tells us we must retain the cosine square root of 16 pi k phi term, or phi tilde. Yeah. Because for delta equals 1, k is a half, so this becomes cosine square root of 8 pi phi, which was precisely the point in this perturbed free boson theory when the Kosterlitz-Thouless transition appeared. Okay? So from what we had seen before, the Hamiltonian of this XXZ chain, when delta goes to 1 minus, is Vf over 2 integral dx phi tilde squared plus dx theta tilde squared. And then we had a plus lambda integral dx cosine square root of 16 pi k phi tilde. Okay, so now we're very close to here. Now, let's understand what goes on in the lattice model, lattice spin model. So the Kosterlitz-Thouless flow diagram that I had drawn for you is somehow looked like so. Yeah, and then here we had this crossover flow. Yeah, and so we had something like Z parallel, Z perp. Remember this. Yeah, so that was the flow diagram for that theory. Okay, now we have to figure out where the lattice model sits on this flow diagram. Yeah, so now because we are approaching delta equals 1 from less than 1, yeah, you can convince yourself you're actually sitting somewhere here. Okay, so this interaction for delta goes to 1 minus is marginally irrelevant. So it eventually flows to 0. Sorry, I'm actually, so in the limit, I'm on this trajectory here. So I'm going down here. So it's marginally irrelevant. And when delta is a little bit less than 1, so I would be on one of these trajectories. Okay, that's what I was saying before. So I'm precisely on this trajectory. So this is the XXX chain. Yeah, so at low enough energies, I still become a free boson, SU2 invariant free boson. In that case, I can use the Lange-Liquid description to compute correlation functions, etc., etc. But the price of having this marginal perturbation now is it's marginally irrelevant. It still flows to 0, but it's marginal, so scaling dimension is 2, is these correlation functions I had written for you earlier, which were these power laws. They acquire multiplicative logarithmic corrections, which one can compute, but I'm not going to do it for you. Okay? So, on the other hand, if delta is a little bit larger than 1, so if I do delta equals 1 plus, I'm on this trajectory. So let's see, green, I would be on this trajectory. Yeah, and there the perturbation is marginally relevant, and a gap opens up, and I computed for you how to estimate the gap. So this gap would open up, would be exponentially small in delta minus 1. So it would be a very, very small gap would open up, and a very large correlation length would develop, but finite. Okay, and then if delta is larger than 1, you would be on trajectories like this. So this cosine perturbation would be relevant, yeah, and you generate a finite correlation length. So in other words, here at 1, I'm still critical. It's a Lange-Liquid, very nice, special Lange-Liquid SU2 invariant. Here, I have a finite correlation length. Yeah, and so what is the physics of this large delta phase? I can no longer compute it using bosonization because I have a gap, I have a finite correlation length. But the physics of that phase we can understand very easily by basically just doing the following. So the Hamiltonian is essentially J sum over J Sx Sx plus Sy Sy plus delta Sz Sz. Something like this. Okay, and so the physics is the same for all delta larger than 1. So there's no other transition along this line, turns out. So we can understand what is the physics here in this regime by just considering the large delta limit. Yeah, so what is the physics of the large delta limit? I just decided earlier I'm going to ask you more questions, so there you have one. Yeah. It's an Ising antiferromagnet. So what does that do? Okay, so it orders, and is that allowed? We're in one dimension. No boundary conditions. We're talking about spontaneous symmetry breaking, so we're in the infinite volume. Yeah. What is the symmetry of the Ising antiferromagnet, of the Ising classical Ising model, or this? Okay. Sorry. It's a Z2. It's a discrete symmetry. Yeah. And as I mentioned to you, kind of like ages ago, probably in the first lecture. So in one dimension at 0 temperature, you are allowed to spontaneously break discrete symmetries. So a Z2 you're allowed to break. Yeah, and so I'm allowed to have kind of like the same physics as you have in the Ising model to break the spin rotational symmetry around the x direction by pi. Yeah, so I'm not allowed to break the spin rotational symmetry around the z direction because that's a continuous symmetry, it's a U1 symmetry. So Mermin Wagner Hohenberg tells me I can't do that. But I also have this discrete symmetry, which I can think of as a rotational symmetry around the x-axis by an angle of pi. Yeah. And that would send Sz to minus Sz. Yeah, so that I'm allowed to break. And so then you can have this spontaneous symmetry breaking, Néel order. So you get, let's say, a ground set up, down, up, down, up, down, something like this. And you have an order parameter in the infinite volume. Okay, so what happens here, you essentially have antiferromagnetic long-range order in the infinite system. Yeah? So now, just because we're talking about all these things, so what happens in a finite system? Because people keep on talking about boundary conditions, etc., etc. Sorry, you had a comment? Yeah. But this is not the subject of these lectures, so I'm not allowed to use that in any which way. So, what we said, we have spontaneous symmetry breaking in the infinite volume, so we have Néel order, blah, blah, blah. So what happens if I have a very large spin-half Heisenberg XXZ chain for delta larger than 1 on a ring of L sites? Well, you raised your hand, or you were just scratching yourself? Okay, so... No, I don't use perturbation theory for that. I like perturbation theory, but not for that. There is no spontaneous symmetry breaking, yeah? But what happens instead? Sorry? Yes, but in terms of eigenstates of the Hamiltonian. So how does the Hamiltonian tell you, in the infinite volume, I really want to break my symmetry? Yeah, but for the finite ring of L sites, the Hamiltonian already tells you, if you're willing to listen, yeah, that it really wants to spontaneously break some symmetry. Sorry? Yes, but you're not allowed to answer. Yeah, okay, so there have to be two low energy states which are almost degenerate. Okay, and the way it works for periodic boundary conditions is you have the ground state which has momentum 0, and you have the first excited state which has momentum pi, and the splitting between these is exponentially small in system size. Yeah, so delta E goes like e to the minus alpha L. Yeah, so they're almost degenerate. So the way to think about these in terms of these simple pictures, so this one you can think of up, down, plus, down, up, down, up, down, up, and the other one like this, and they're almost degenerate but not quite. So that's what happens on a ring with periodic boundary conditions. What happens on the open chain with open boundary conditions, you again have two states which are almost degenerate. Yeah. And in this case, so the splitting again is exponentially small, and the difference between those two, in one of them you would have some boundary state. I mean, so there would be, H state, sorry. Okay, so the way I see the splitting, I saw the spectrum exactly. So what I had in mind is, because probably all of you like computers, so you can compute the spectrum using iTensor or something like this, yeah? And then iTensor basically would tell you there's this splitting, and then what you know now, because apparently you didn't know it before, that how I tensor tells you that the system will spontaneously break a symmetry in the infinite volume, right? Because of this story. Okay. That was a bit of a tangent. I actually didn't really want to talk about it, but okay, fine. So that's what happens in the antiferromagnetic region. So by the way, when am I supposed to stop? Okay, yeah. Yeah, okay. So you see, I could keep on going for quite a while, but okay. So what I want to talk about a little bit, what happens when delta goes to -1. So when I approach this Heisenberg ferromagnet, and this is much more subtle now, yeah, because, okay, so here, what happens is the Fermi velocity actually goes to 0. Okay, and when the Fermi velocity goes to 0, so the theory signals to you, I'm approaching a phase transition, it could be a first order phase transition, so something drastic happens. So this is the theory's way of telling you, my regime of validity is disappearing. Yeah? So now, in order to get a little bit of an intuition about what that means, is we do the following considerations. So this signals, firstly, that the QFT description is valid only at very low energy and very large distances. And it also signals that the QFT description is about to break down. Okay, so whenever you have free boson theory with a tiny velocity, you have to be careful. So now, how to understand this, these statements? So remember, so the Fermi velocity, it's related to the propagation velocity of some collective excitation. Yeah, in terms of the bosons, this is some collective boson mode. In terms of the fermion, it was really just fermionic excitations around plus or minus kF. Okay, but in the interacting theory, so these are some kind of complicated collective modes. But so let's understand, however, what it means for the velocity to be tiny. Okay, so let's start by just looking at the fermion model. Yeah, so there we had kF and minus kF. Okay, so now if I have a small velocity, it means that I have something like this. Okay, so now remember, in the lattice model, momentum is restricted to the first Brillouin zone. So if you have a tiny velocity, yeah, the energy range in which these collective modes can live becomes smaller and smaller and smaller, because if you go all the way to the Brillouin zone boundaries, you just go to a very low energy. Okay, so this kind of gives you some intuition why, if the velocity is low, you describe the physics only at extremely low energies. Yeah, because of course you get this, you get the Fermi velocity by linearizing the dispersion, and the regime over which the dispersion is linear is much less than all the way to the Brillouin zone boundary. So this gives you an upper bound. Now, If the theory only holds at really, really low energies, so then you can use basically the fact it's relativistically invariant, etc., etc. It can only hold at very large distances. Okay, and so it basically means if you look at something like a ground state correlation function, Sxj or S alpha j plus L, ground state, you will get some answer here, 1 over L to some power, whatever, from the Langer liquid description. But this will be valid only now, strictly speaking, in the limit L goes to infinity, so it's an asymptotic result. And if you want to match this to something you get by doing numerics on the lattice model, the distance you might have here becomes larger and larger and larger the closer you get to -1. Yeah. So if you do numerics, let's say here, then the results you get might fit the Langer liquid description if the distance is larger than 100 sites or something like this. But if you're very, very close, you would have to go to 1,000 or 10,000 sites to see this kind of power law. Okay, and this all has to do with the fact that the theory itself, you can think about it, you have a cutoff in the theory, the cutoff actually collapses to 0. Okay, now, all right, so I tell you one more thing. So I have in principle 10 more minutes, so maybe I can do it a little bit faster. So now I'm going to finish with a topic which is a little bit more advanced. But it ties very nicely to what we have done with the Kosterlitz-Laurus transition and this Wilsonian RG and so on and so forth. So what I'm going to do now is I'm going to sketch for you how one obtains famous formula Haldane obtained for bosonization. From this framework that we have developed. So I call this low energy projection of operators part 2. And part 1 was what we had done before. So in the free theory, we had something like Cj was square root of A naught, right of x, e to the I, kfx plus left of x, e to the minus I kfx. Okay? And that led us to understand that if I look at the two-point function of fermions, I will have oscillations that go like e to the I kfx, e to the minus I kfx. But for example, there would be no oscillations that go like e to the 3 I kfx or e to the 5 kfx, etc. So in the interacting theory, it turns out there are additional contributions. And I'm going to explain to you now where they come from, yeah, and how to handle them. So in most circumstances, let's say, if you do this kind of stuff that we have been doing, it's enough. But for certain applications, you miss something which is important, yeah, and then you have to basically understand what I'm going to tell you now. So what we want to do is have some Wilson RG-like consideration. So what we have in mind is, okay, so we want to project this lattice fermion, and at some intermediate kind of length scale or energy scale, this gives me some quantum field. And this quantum field, so it could be something like this at very low energies, but now I have in mind I'm not at very low energies yet. So this field then I treat a la Wilson. So I say this has a piece which are high energy degrees of freedom, and a piece which has low energy degrees of freedom. Okay? And now, so this is very similar to what we had done in the RG. So, and let's say the interaction Hamiltonian would be something like this. What I should have said, okay, so these I now treat in some path integral language, and I have now fermions, so this relates to Grassmann variables, whereas before I was doing it for bosons, but so here I get something like this, so psi dagger of x, psi of x, psi dagger of x plus a naught, psi of x plus a naught. So I take my interaction Hamiltonian like so. Yeah, it's the same form we had for the spinor half chain, which was c dagger c times c dagger c. Okay, and then we now do this decomposition. So this gives us a very large number of terms. And I'm just going to write down one because I just need the structure to motivate what I'm going to do. So let's say I take the high energy part here, and then the low energy part of the others. Okay, so then I would have psi lower of x, psi dagger lower of x plus a naught, psi lower of x plus a naught. And then we have many, many, many other terms which involve this low and high energy degrees of freedom. Okay? So now what I do is just like we did in the RG, so we integrate out the high energy degrees of freedom. Yeah? So on the face of it now, it looks very much like what we had done for the Wilson RG, but just for fermions. Now the difference is, now I want to consider not the action, but I want to consider an operator. Yeah, so I'm interested in working out what is the low energy projection, and I get this by basically saying, aha, so this is psi larger plus psi less, and then here I have the action corresponding to this interaction Hamiltonian, yeah, and I want to take the average with respect to the high energy degrees of freedom. So this is what we called the average over these H fields in the Wilson RG earlier. Okay? And so the kind of change to what we had before is now I average this operator. Yeah? Whereas before we were just looking at the effective action. Okay, so what does that give? So that gives many contributions. I'm just going to write down one, gives terms like so. Lambda, okay, psi larger than 0. Here's an expectation value. So I look at this one here. And then here I get integral dy d tau, and I probably have a minus sign. And here I have a psi dagger larger of tau y psi less of tau y psi dagger less of tau y plus a naught psi less tau y plus a naught plus many others. Terms like this one. Yeah. You see, this corresponds to what the term I had selected here. So I have one of the fields which corresponds to the creation with high energy degrees of freedom. All the others had low energy degrees of freedom. Okay, so now the average is with respect to the high energy degrees of freedom. So what I will get is just the Green's function corresponding to the psi dagger. Yeah, and this is some Green's function minus tau x minus y. Okay, and importantly, this is short-ranged in both tau, so imaginary time, and the distance, which means I can take this integral over y and tau because the Green's function is very, very short-ranged. And what that does, it basically sets the arguments of these three fields to be the same as what I had here, namely, so y becomes x and tau becomes 0. So this generates a term lambda times some coefficient, which I get from integrating the Green's function. And then I get what I was after. I get something like psi less of x, psi dagger less of x plus a naught, psi less of x plus a naught. Okay? So now, you see, by doing this, we have generated a new contribution to the low energy projection of our operator. Yeah? And now you can remember the psi and the psi dagger at low energies. I should think in terms of left and right moving fields, yeah, with kf and minus kf. But now I have terms which are cubic in these fermionic fields. That will generate contributions to the low energy projection of the fermion operator, which come with e to the 3i kfx and e to the minus 3i kfx. So these are called higher harmonics, and then by repeating this procedure, looking at higher and higher orders, you generate all higher harmonics. Okay? And I've explained to you now where it comes from, and I have minus 30 seconds. So if you carry this out in full, then what you find is Cj is square root of a naught. Now you have an infinite sum of terms. So originally we had two, yeah, so the left and right moving fermions. But now we actually have all the higher harmonics. I can write it like so, e to the I kf x 1 minus 2n. And then here we have e to the I minus I square root of 4 pi phi right. And then here we have e to the I square root of 4 pi n phi. So that is the full formula. So the leading terms in this are again the right moving Fermi field, which you get for n equal to 0, and the left moving field, which you get for n equals 1. But then this also incorporates now all the higher harmonics. Yeah? And each of these harmonics comes with some non-universal coefficients, which depends on the detail of the lattice model you're considering. And so a formula like this, derived in a completely different way, was first suggested by Haldane in his paper, as I mentioned. And then I've run out of time, so I stop here. Yeah, okay, so thank you for your attention. And that's it.